Hi everybody. We'll talk a little bit more about averages and probabilities. So I'll consider some aspects of quantum measurements. Suppose for now a spin half system, okay? A Hilbert space for simplicity n equals to 2, spin half. Hope you did the math with the Pauli spin matrices. So we'll talk a little bit more about spin half because it's very interesting. It's a very pure quantum mechanical system. It's simple because matrices are just 2 by 2 matrices. It's easy to do the math. And consider, for instance, that a physical system is just spin half particle. And I am not interested in talking about position and momentum and none of that. I'm just wanting to measure spin. So I can perform Stern-Gerlach type or Gerlach type of experiment. All right. And well, okay. So you can perform Stern-Gerlach type of experiments measuring the electron spin. Nothing about position and momentum and all that. So your Hilbert space is a space of dimensionality equals to 2. Just a discrete space. It's easy to do the math, right? So consider this initial state. Initial state. Psi, I prepare a state. How do I prepare the initial state? By measuring preparation is equal to measuring first round. Okay, so a first time. Okay, so we would have a beam of electrons, an electron beam, isotropic in spin. You have spins in arbitrary directions. You make it pass through a Stern-Gerlach experiment. So you have electron beam. Here you measure sigma of x first. Okay, so you are measuring spin in the x-axis. So you will find two possibilities. So this is an electron beam at a high temperature. Initially, they performed the original experiments with silver atoms, which the only relevant parameter for the experiment was the electron spin of the outer shell, which is a NS, one electron in an S orbital. The N, I don't remember the number here. I guess it's 5 or 4, but it's silver usually. So you evaporate silver atoms, you make them be collimated, you select velocities, so the velocity of the electrons are very well controlled, and they pass through a magnetic field gradient. It must have a gradient in the magnetic field, and the beam is split into two possibilities, h bar over 2 plus and the minus h bar over 2. This is what you find, and you block this state here, you just select this one, and this one will be corresponding to your prepared state. All right, so you have electrons which have this, for certain, this state. It corresponds to the x plus, measuring the x-axis, the plus state, the h bar over 2. But if you did previous exercises using Pauli matrices, you would find that this matrix, this sigma of x equals to 0, 1, 1, 0, you would find there are two eigenvalues, the plus and the minus, and the plus is equal to 1 over square root of 2, 1, 1 here, and relative to the sigma z basis, or the spin in the z direction, it corresponds to 1 over square root of 2, the up in the z direction plus the downstate in the z direction. I could put z here just to remember that this basis is the basis which diagonalize the spin operator in the z direction. So the up state, I'll not be writing z. So the up state is 1, 0, and the down state is 0, 1. So we can sum these two things to obtain 1, 1. So it's up plus down. It must be normalized to have modulus 1. So it's the square root of 2. All right? So this is the preparation of the state. You make whatever, pass through a measurement system. The example is electron beam, and you block what you do not want to be and let pass what do you want to measure. So that's preparation of the state. And consider that our initial state is electrons with up spin in the x axis, relative to the x axis. All right. Well, I'll make a parenthesis in the discussion here, because if you calculate the eigenvectors, suppose you have a general eigenvector of non-normalized numbers, say C1, C2, C3, and so on, Cn here, or psi, okay, psi1, psi2, and psi3, psi n here. You have a lot of numbers here. But if you calculated first the modulus of this vector, you'll find bigger than 1, not normalized, or perhaps less than 1, right? At first, if you do that, right, the state is not normalized, and you need to normalize the state. So what you do, you define a psi, say psi prime, which is the previous psi divided by square root of this thing here. Then you'll find out a normalized ket state. So to normalize, just divide by the square root of the modulus squares, if previously unnormalized. Sum them up, take the square root, multiply by your initial number, right? These are numbers, and you'll find a normalized ket. So if you are calculating the eigenvectors of the sigma of x, the Pauli matrix in the x direction, you would find the vectors such like 1 and 1, right? But this is not normalized. So you take the square root of the sum of the squares. 1 plus 1 is equal to 2. Right? Also, if you are calculating, if I remember correctly, the eigenstates of sigma of y, which is this matrix, minus I, and zeros in the diagonal, you would find the plus state in the y direction, which is the plus one eigenvalue corresponding to this eigenvector. If I remember correctly, it is just the square root of 2, 1, and I, the imaginary unit. But notice, you could find 1 and I, or another combination of numbers, but non-normalized. So you normalize it. The normalization uh, comes from taking 1 over the square root of 1 modulus squared plus I modulus squared, but the I squared in modulus is equal to 1, so the square root of 2 here. All right, so this is a trick, an easy way to normalize vectors. When you calculate eigenvectors, you do not worry about normalizing it at first, because when you find the eigenvector, you can calculate the projection. If it's not equal to 1, you just need to divide the vector you have found by the scalar product, the square root of that. It corresponds to the sum of the squares, the modulus of the squares. Beg your pardon. This is the summation of squared modulus of the components of the vector, and you take the square root, you normalize the vector. All right? Well, let's go back. So we prepared the state. The state is prepared at first in the x direction. It's up plus down. So I have, I don't know what. We had a probability, but I measured sigma of x. What gives me the down state I blocked here, physically blocked here in this case, and let this beam pass. And I can confirm. Notice that here I have a lot of states, distinct states of spins. But when I measure, I make the system collapse to one of the eigenvalues of this operator, which would be down and up states relative to that axis. In this case, the x-axis. So I can perform, so this had a previous probabilities. I am considering only after that I can confirm by a second measurement of sigma of x, and I'll find what? I'll find 100% sure up in the x direction. I'll find this state 100% sure after second measurement, because I already measured, I separated the beams, physically separated, I prepared the state, so I can confirm that my physical state is in this condition, and it will follow. You will have 100% of up states. All right, so the state's prepared. Now, if you have this thing here, you prepare the state, you can pass it. So psi, you can pass it to a sigma of z measurement system. It's just rotating the magnetic fields to perform the new measurement in the case of spin. And in this case, you'll find, so here you have 100% of plus or up in the x direction. But this is not an eigenstate of sigma z. It's not an eigenstate of spin in the z direction. It's an eigenstate of the spin in the x direction. It's up, it's down. So, what are the probabilities here of measuring the up state, okay, the h bar over 2 negative is up state in the z direction, relative to z direction, and plus relative to z direction here. What are the probabilities? I can just make a calculation. Given the state psi, what the probability of measuring up? And the probability is calculating by projecting the state I want onto the state of the physical system modulus squared. All right? So if you project that, notice by the orthogonality of the basis, the projection of up onto itself gives 1, onto the other state in the z direction gives 0. So I will have 1 over square root of 2 squared, and this will give 1/2. So I will have 50% chance here. And the same, if you calculate given psi chance of measuring down, you make this calculation, you find half, which means as a percentage, 50% down. All right. So if you have knowledge of a physical system in a initial condition, you can measure the sigma z and you'll find 50-50 chance of having up spin, down spin. But you would demonstrate that the up and down spins in the z directions are linear combinations of the up and down spins in the x direction. So if I block here, I can block here. Okay, it's blocked. I don't have any interest in letting it go forward, so I block, physically block this beam. These are physically separated in case of spins. Spin up goes up, say, and down goes down, so they are separated. If you measure in the x-axis, you have one beam goes that direction, the other that direction, so they separate physically. And you can measure again sigma of x. What are the probability of having up in the x and down in the x direction? If classical physics apply, then you would say, well, I already measured the x component of the spin, and I am 100% sure it's up, it's the plus state in the x direction. But in quantum world, the order of measurements are relevant. So when you measured the sigma z, the spin in the z direction, you completely destroyed the previous information. And in this case, you will find out 50-50% chance of finding up state or down state in the x direction. Classically, you would expect to find 100% here because you prepared initially the state in that condition. But quantum mechanically, you know sigma of x does not commute with sigma of c. This is distinct from zero. It's not zero. So the order of measurements are important. And when you measure sigma of x a second time, but after I measured the sigma z, I destroyed the previous information. And I found, and I must find 50-50 chance. All right. You could rotate. You could rotate your apparatus of measurements, and this is very similar to measuring, to perform a measurement of light polarization state. If you put a filter, a polarization filter, which pick up light with linear vertical polarization, and you just pass it through a vertical filter, you would have 100% of light polarized in the vertical direction for the electric field. And if you put a second polarizer rotated, so in the first filter, you blocked the light with horizontal polarization. You blocked that component. But if you put a filter rotated not at 90 or 0 degrees, in the middle of another measurement of vertical or horizontal polarization, say horizontal polarization, you lose the information of the first measurement. So this is analogous to the measurement of light polarization. Sakurai has a discussion about the analogies. I recommend you read the book. All right, you can read it. Well, so 50-50 chance. Why is that? Because if you calculated properly, the x up state corresponds to 1 over square root of 2, 1, 1 for the cat state, which you can represent this way, up and down, and x minus is just change in sign here for the second. You will find out this thing here, minus down here. These are the spin states relative to the z-axis. So if you would write, sorry, it's up here. If you would write the up state in the z direction, you can sum up these two equations. You'll get the down state eliminated, and you get twice this, but twice divided by the square root of 2 is square root of 2. You can divide. So you'll find square root of 2 here. In the x direction, the up state, plus in the x direction, the down state. Right? So also the down state, you can demonstrate, you can subtract. So 1 over square root of 2, x plus minus x minus, right? And notice that in that measurement, if you measure first the x component of the spin and you block the down state, you would find 50-50 chance of measuring up or down in the z direction. But when you block the down states, you will have 100% sure, it's another preparation, that your system is in the up state in the z direction. And this up state is, again, 50-50 chance of spins up and down, but in the x direction. So you destroyed the previous information which stated that the physical system was in the up relative to the x axis. All right? So when you measure, if the operators are not compatible, you destroy previous informations when you measure another operator. Okay? You would calculate what will be the intensity of the axis, the beam, better said that way. Suppose you prepare the state measuring a previous x components of the spins. You get up in the x direction and down in the x direction. You block the state, okay? This is the prepared state. This is equal to the psi, which you started with. It's a collection of electrons with this state, as a matter of fact. And you make it pass through a sigma z measuring system. And in this way, you will find 50-50, up and down, right? Up and down. And you can block the down state or the up state, doesn't matter. You choose. And now you have an up state, right? You have an up state. And you decide to measure again the sigma of x. What is the probability of finding the down state in the x direction and the up state in the x direction? 50-50, because of the linear combinations we showed just a moment ago. So notice you have a chance of finding now the system in the down state, but you blocked this state initially for electrons previously prepared with the down state. You blocked. You only had electrons passing through here with up spins with respect to the x-axis. But you are measuring an incompatible operator with this one. And in this case, you'll find a chance again because you destroyed the previous information. And if you block now this, the up state now, you would ask, what is the intensity of the beam here? Well, if you consider this, the first preparation you don't count. If you consider this as 100%, the total of the beam, when you pass through a first Stern-Gerlach experiment, you cut half of the intensity here, just letting half the intensity in this branch, which corresponds to the up state of z spins. And now, if you let it go, let it pass forward only the down state in the x direction, you cut another half of this previous. So you would find what? 1/4 of this 100%, right? And you can calculate all the uncertainty relations. So, for instance, if you have this state here, 1 over square root of 2 of up in the z direction, down in the z direction, you can calculate the average of sigma of x, all right? You plug in the matrix, the vector, psi here, you find this is equal to 1, the plus 1, right? Because you are 100% sure in this case that your system is in the up state of sigma of x. So it just gives you the plus eigenvalue and the normalization, because sigma x applied to the plus 1 eigenvalue just gives you the eigenvalue and repeat the eigenstate. So this gives, it's normalized, it gives +1. But if you measure the sigma of z, all right, you'll find half, you can do the math. So, but physically, you find half with up and half with the down, the -1 eigenvalue. And since these are same amplitudes, but opposite signs, 0. Okay, so you'll find that the average of sigma of z, right? The average is 0. The average of sigma of x is +1, all right? Well, and you can calculate the sigma of x squared and take the average, and you can calculate the sigma of z squared and you can calculate the average, but sigma of x squared is just the identity matrix. You can show that, and same for the sigma z. So this will be 1, this will be 1. So when you calculate the delta of sigma x, you'll find the average of the square minus the square of the average, and this will give you the numbers. So also for delta of z, okay? And in this case, square root of this thing, z here, here, you'll find the values, all right? And you can calculate, you can demonstrate the uncertainty relations for spins, all right? So, for instance, the delta of z, and the delta of x, and the delta of sigma z must be bigger or equal to 1/2 modulus of the commutator. In this case, you can do the math with the given state psi initially prepared. All right? Also, another interesting thing you must calculate with Pauli matrices, which is a very, very interesting problem in quantum mechanics, is the generalization of this thing in complex algebra. If you pick I, the exponential of I theta, you'll find cosinus of theta plus I. It's just a scalar, a complex scalar. But for a Pauli matrix, this is a generalization of that relation. If you pick this thing, it's a relation which you can calculate using an expansion. Just the 2 appears here because theta of 2. This gives you 1/2 factorial. The imaginary goes inside here, and you divide it by 4, and so on. You'll find out sinus of half the angle, multiplying the identity matrix plus now the imaginary unit must be replaced by the Pauli matrices multiplied by the imaginary, sinus of the half this parameter theta over 2. All right, this is a very important relation in quantum mechanics using Pauli matrices. All right, so you must demonstrate this thing. This is a very interesting result. It's a generalization for Pauli matrices. Also, I said previously that you need to have profound knowledge of matrices, but if you are trying to exponentiate a matrix, suppose exponential of a matrix A, you must consider it as an expansion identity, a Taylor series plus the matrix squared over 2 factorial plus 2 over 3 factorial, and you must go to infinity. So this corresponds to the summation over n from 0 to infinity matrix over the exponent n divided by n factorial. This is the exponential of a matrix. Okay? Another way is to use the Eigen Vectors of A, and you use as a basis the Eigenvectors from 1 to n, suppose j here, or alpha, it's better to use alpha here, alpha from 1 to n, the exponential multiplying, this is the resolution of the identity in a given basis. So you'll find that the exponential of a matrix corresponds to the exponential of the eigenvalues, exponential of an eigenvalue from all the eigenvalues from 1 to n, alpha. That's computers usually perform the calculations of eigenvalues and eigenvectors of this matrix and insert the resolution of identity here and calculate that, and then if needed perform a basis transformation for giving you the final answer. So the exponential of a matrix can be calculated this way as a Taylor series of the matrix of the exponential considering matrices, or this way. Okay, many computers, when you use computers to calculate things, would exponentiate each of the inputs of the matrix. It's different. Okay, if you have a matrix, for instance, consider a matrix A equals to 0, 1, 1, 0, and you want to exponentiate the matrix. Okay, this is different. The exponential of this matrix is different to taking e to 0, e to 1, e to 1, e to 0 is different from that. All right, you need to perform the calculations. You need to expand the matrix. So you will have a to the exponential of a is equal to the identity matrix plus the matrix plus 1 over 2 factorial, the matrix squared, you need to calculate that. All right, that's an important issue when dealing with matrices. Well, for now that's it. We need to talk about also the uncertainty relations for position and momentum. It has to do with Fourier transforms. So in the next video we'll talk about that. Right. Bye bye.